So imagine you are, you know, just cruising down the highway at like 70 miles an hour in a modern electric vehicle.
Right.
Beneath your feet is this battery pack that's so incredibly dense,
Yeah.
so massive, that it essentially holds enough raw energy to, well, to power a typical house for an entire week.
Yeah, the scale of it is pretty wild when you stop and think about it.
It is.
Yeah.
And the sheer, like, brute force required to take a heavy vehicle from 0 to 60 in under 3 seconds, I mean, that's just staggering.
Mm-hmm.
But the thing that really gets me is that the only thing standing between that raging high-voltage river of energy and a catastrophic, just total loss of power at highway speeds is a tiny switch,
Mm.
like about the size of your fist.
Yeah, it really puts the scale of modern engineering into perspective.
Yeah.
Because you're dealing with hundreds of amps of current
Right?
and hundreds of volts of electrical pressure. And you're completely right. Like, while everyone obsesses over the giant motors and the fancy battery chemistry, the entire system relies entirely on this one relatively small component.
The high-voltage main contactor.
Exactly. Or, simply put, the main relay.
And the stakes with this switch, they really couldn't possibly be higher. I mean, if this little box fails, the absolute best case scenario is that your car just, refuses to start in your driveway.
Right, you're just stranded, which is annoying, but safe.
Exactly. But the worst case scenario, the absolute nightmare, is that it unexpectedly loses power while you are navigating high-speed traffic.
Yeah.
And in the automotive engineering world, they classify that kind of unexpected power loss as an ASIL D safety risk, Automotive Safety Integrity Level D, which is, if I have this right, that is the highest, most critical risk classification that exists.
It is. Yeah, when a system is rated ASIL D, you are no longer just designing for, normal everyday operation. You are essentially designing a system that must survive extreme catastrophic failure modes.
Wow.
You have to guarantee that even when physics and chemistry and the actual environment are actively fighting to destroy the component, the system fails in a way that keeps the driver entirely safe.
So today, we're basically cracking open the playbook on exactly how engineers actually pull that off. We are diving really deep into the anatomy of a specific, terrifying fault condition known as a stuck-open contactor.
Mm-hmm.
We're going to deconstruct how engineers predict these microscopic failures, how the car's computer diagnoses them, I mean, faster than a human can even blink, how the hardware is armored against disaster, and then the apocalyptic torture tests these parts have to survive before they're ever allowed near a consumer. It's essentially this high-stakes engineering detective story.
I like that way of putting it. And, like any good detective story, if we want to understand how to build an indestructible safety net, we first have to understand the mind of the killer, right?
Oh, totally.
We have to look at exactly how this component breaks down under pressure.
Okay, so let's unpack this.
Yeah.
Because a contactor getting stuck open, which basically means the switch is supposed to be closed and conducting power, but it's physically trapped in the disconnected position. That isn't just like one simple part snapping in half.
No, not at all.
It's a chain reaction. So let's start with the first way the universe tries to destroy this relay, the heat trap.
Right, the heat trap. So to understand this, you really have to look at how this switch actually works at a basic level. The contactor is operated by a low-voltage coil. It's basically just a simple electromagnet.
Okay.
You run a small current from the car's standard 12-volt battery through this coil, and it creates a magnetic field.
Got it.
And that field physically pulls the heavy high-voltage contacts together to close the circuit.
Sounds simple enough, right? Just run 12 volts and you're good.
It does sound simple, yeah, until you realize that a car's 12-volt system is actually incredibly messy.
How so?
Well, it is almost never exactly 12 volts.
Right.
Yeah, depending on what the alternator is doing or the DC to DC converter, or, if you just suddenly kick on the air conditioning, that voltage is constantly fluctuating. It can be anywhere from, say, 9 volts all the way up to maybe 16 volts.
Oh, wow. I never thought about that. And the math in our sources here shows that this fluctuation is actually deadly if the system isn't carefully controlled. There's this principle of electrical heating where the heat generated scales with the square of the current.
Yes, joule heating.
Right. So if the voltage spikes and the current increases, the heat doesn't just go up, a little bit, it skyrockets exponentially.
Precisely. And this heat is trapped deep inside the dense windings of the coil, because the copper wires inside that electromagnet are coated in this microscopic, razor-thin layer of enamel insulation.
You're basically paint, right?
Essentially, yes. It's
Yeah.
a special paint. And if the coil is subjected to continuous exponential heat generation, that enamel suffers from severe thermal aging. It literally cooks.
Oh, man.
The insulation gets brittle, it cracks, and eventually it just flakes right off.
Wait. If the enamel flakes off, that means you just have bare copper wires pressed up against each other inside the tightly wound coil.
Yes. And as we know, electricity will always take the path of least resistance. So when those bare wires touch, the current skips an entire loop of the coil. Engineers call this a turn-to-turn short.
Oh, so it's taking a shortcut.
Exactly.
And if the path is shorter, the overall electrical resistance of the coil drops. And if resistance drops, then more current rushes in.
You've got it. It's a textbook thermal runaway event.
Well, that sounds bad.
It's very bad. More current means even more heat, which then melts more of the surrounding enamel, which creates more bare wire and more shortcuts. It just feeds on itself.
Wow.
Eventually, the heat gets so intense that it acts almost like a soldering iron. It physically melts the copper wire right in half.
Jeez.
Yeah. The circuit breaks open, the current stops dead, the magnetic field instantly vanishes, and those heavy high-voltage contacts, they just slam open, and power is lost.
So it's kind of like holding a heavy fire door completely open with one arm for hours.
Yeah.
You can do it for a little while, but eventually the strain builds up, your muscle gives out, and that heavy door just slams shut on its own.
That is a really brilliant analogy. The electromagnet is your arm, and it just gets too exhausted, too thermally degraded, I guess we'd say, to hold the heavy electrical door open anymore.
So that's how heat kills the system.
Yeah.
But the second root cause of failure that we were looking at, this one really threw me for a loop. It's this electrical backfire.
Ah, yes.
The engineers found that the tiny microchips, the silicon drivers that turn this 12-volt coil on and off, they were physically blowing up. And they were blowing up because of massive voltage spikes. Now wait, I'm completely stuck on this detail.
Sure.
You just said this coil runs on a messy 12-volt battery. How on earth is a simple low-voltage circuit generating a spike big enough to physically destroy a microchip? Like, that makes zero sense to me.
It is highly counterintuitive, I'll give you that. But it all comes down to a phenomenon we can call electrical inertia.
Okay, inertia.
Yeah. Think about what an inductor, which is what a coil of wire is, actually does. When you flow current through it, it creates a magnetic field. But that magnetic field isn't just magic, you know? It represents stored physical energy.
Okay, so the energy is just kind of hanging out in the space around the coil.
Right. Now imagine you suddenly turn off the transistor switch to stop the current. You want the relay to open, so you break the circuit. That magnetic field suddenly has absolutely nothing sustaining it, so it collapses incredibly rapidly.
But the energy has to go somewhere, right? It can't just vanish into thin air.
Exactly. And the physics of a collapsing magnetic field try desperately to keep the current flowing in the exact same direction. Because you shut the switch off instantly, the time it takes for this change to happen is microscopic.
Oh, I see.
When you compress all that collapsing magnetic energy into a tiny fraction of a second, it generates a massive reverse voltage spike. To visualize this, think of the water hammer effect in household plumbing.
Oh, like when you run the faucet on full blast and you slam the handle shut really fast and you hear the pipes violently bang inside the walls.
That is exactly it. Water is heavy, it has mass and momentum. When it's rushing through the pipe and you slam the valve shut, all of that kinetic energy doesn't just disappear.
Right, crashes.
Yes, it crashes into the closed valve, creating a high-pressure shock wave that ripples back through the pipes. In our electrical circuit, the magnetic field is the momentum of the water. Suddenly shutting off the microchip is slamming the valve.
And that shock wave is the electrical backfire we're talking about.
Yes. Normally, circuits have a specific component called a flyback diode.
Okay.
Its entire job is to act like a pressure relief valve. It gives that collapsing energy a safe, circular loop to travel through so it can gently bleed off its momentum.
But if that little diode fails...
Then the electrical pressure wave, which can momentarily reach hundreds of volts, by the way, has nowhere to go. It crashes headfirst into the fragile, low-voltage microchip and literally blows the silicon wide open.
Wow. And once the chip is blown, the door is permanently shut. You can never turn the relay back on.
Nope, it's dead.
Okay, so we've got heat melting the wires and electrical shock waves exploding the control chips. The third way this thing dies gets into the purely physical realm, which is the mechanical grind.
Yeah, this brings us out of the theoretical physics and into the brutal, harsh reality of a moving vehicle. because a car is an incredibly rough environment.
Right. It's not a laboratory.
Exactly. You have constant, random, high-frequency vibrations from the road, from the drivetrain, the chassis. We're talking vibrations ranging from 100 hertz all the way up to 1,000 hertz.
1,000 hertz is intense. I mean, that's not just driving over a pothole.
Yeah.
That is a constant, aggressive buzzing that's just penetrating deep into the component.
Right. And inside this relay, you have a solid iron core that has to slide back and forth inside a guide tube every single time the switch opens or closes.
Okay.
When you subject that sliding core to 1,000 vibrations a second, it causes something called fretting wear.
Fretting wear.
Yeah. It's a microscopic high-frequency rubbing that slowly, mercilessly grinds away the surface materials. And over time, it generates this fine, abrasive dust of metal shavings and metal oxides.
Oh, that sounds terrible. But the data shows it gets significantly worse, depending on the weather, right? Like if you introduce extreme cold, like negative 40 degrees Celsius in the dead of winter, the physics change again.
Because automotive seals are almost never perfect over a 10-year lifespan. Let's say a tiny amount of moisture from condensation gets into that guide tube, or maybe a microscopic trace of oil. At negative 40 degrees, that moisture, that oil, and that metallic fretting dust all combine and freeze into a thick, icy, sludgy glue.
Yes. So now the electromagnet turns on, it creates the field, and it tries to pull the iron core to close the switch. But the core is literally fighting this frozen sludge.
The engineering math here is completely ruthless. For the switch to close, the magnetic pulling force must be strictly greater than the force of the heavy return spring that naturally holds it open, plus the force of friction.
Right.
If friction suddenly spikes because of this icy glue and the combined resistance of the friction and the spring exceeds the magnetic force, the core is physically trapped. It will not move. It is stuck in the ice.
Which leads us to the fourth and final root cause of a stuck open failure. And honestly, this one is infuriating because it's essentially a false alarm. It's an issue with the sensor, not the actual heavy machinery.
Yes, the mirror contact micro disconnects. This actually highlights a fundamental challenge in complex safety systems, which is you have to trust your sensors.
Right.
The main computer of the car can't actually see the giant high-voltage contacts. It relies on a tiny, low-voltage auxiliary switch called a mirror contact that is physically attached to the main mechanism.
Okay.
When the big, heavy high-voltage switch slams closed, it drags the little mirror contact closed with it.
And that little switch sends a low-voltage signal back to the car's brain saying, hey, we are closed, the power is flowing, everything is safe.
Exactly. It mirrors the state of the main relay.
But the engineering data reveals that this tiny signal path is incredibly vulnerable, right? Like it can suffer from microscopic corrosion on the contacts or just momentary microsecond level disconnects in the long wiring harness that leads back to the computer. I was thinking about this, and it's exactly like the little plastic light switch inside your refrigerator.
Oh, that's a good comparison.
Yeah. You could slam the fridge door completely shut. The cold air is trapped. The food is safe. The physical door is doing its job perfectly. But if that tiny, cheap plastic switch gets stuck, the brain of the fridge thinks the door is wide open and the light just stays on.
That is exactly what happens in the vehicle. The main computer sends the command to close the relay. The magnetic coil works flawlessly. The high-voltage contacts slam shut, and the heavy power is ready to flow.
Okay.
But because of a microscopic speck of oxidation on that little mirror contact, the low-voltage feedback signal doesn't make it back to the computer.
Oh, man.
The car's brain reads open, it panics, assumes a catastrophic mechanical failure has just occurred, and flags a critical fault, potentially shutting down the entire vehicle on the highway, all because of a speck of rust on a sensor.
Okay, so physics, chemistry, electricity, and simple mechanical friction are all constantly conspiring to freeze, melt, explode, or lie to this tiny box.
Pretty much.
Knowing that the universe is actively trying to break this relay, how does the car's computer catch these failures before they turn into a highway disaster?
This is where the digital intelligence of the vehicle has to outsmart the physical realities we just discussed. The engineers have to build a software architecture that acts as a flawless watchdog. And the primary constraint they're working against isn't computational power, it's time.
The need for speed. The safety standard dictates something called the fault-tolerant time interval, the FTTI. And for this critical power system, that interval is strictly less than or equal to 60 milliseconds.
To put that 60 milliseconds into human perspective, consider this. A human blink takes about 300 milliseconds.
Wow.
If you accidentally touch a red-hot stove, it takes your nervous system and your brain about 200 to 300 milliseconds just to perceive the pain and send the signal to pull your hand away.
That is absolutely terrifying when you put it like that. I mean, the car has to detect a microscopic short circuit, realize the magnetic field is collapsing, understand that the massive high-voltage contacts are opening under load, and safely secure an entire electrical drivetrain 5 times faster than a human can even blink.
It is an astonishing feat of real-time computing. And to achieve that, the system can't just rely on one sensor. It uses multiple overlapping layers of diagnostic intelligence. It actually starts before you even turn the key with OAuth state intelligence.
Right, the smart chips inside the controller. The data shows they constantly inject microamps of current into the coil while the car is completely shut off.
Yeah, they can't send enough current to actually turn the electromagnet on. That would be incredibly dangerous to have the high voltage suddenly engage while the car is parked in your garage.
Right, obviously.
But they send a tiny harmless trickle, just enough to measure the electrical resistance of the loop. Think of a mountain climber gently tugging on their safety rope to make sure the anchor is secure before they step off the ledge.
That makes perfect sense.
If that tiny trickle of current returns an abnormal reading, the chip knows instantly the wire is broken or we have a short circuit, long before the driver ever attempts to start the car.
And when the driver does start the car and the system shifts to on-state intelligence, it gets incredibly aggressive. The sensors monitor the current flowing to the coil continuously. If that current suddenly drops to zero, or if it spikes past a hard mathematical threshold, the control chip physically shuts down the power channel in less than 10 microseconds. 10 millionths of a second.
It absolutely has to. If the current suddenly spikes, it means that thermal runaway we talked about has happened. A turn-to-turn short circuit has occurred.
Right, the enamel melted.
Exactly. If the computer waits even 1 full millisecond to think about it, the heat generated by that short circuit could melt the entire wiring harness or start an electrical fire. 10 microseconds is the electronic equivalent of slamming the emergency brake the exact millisecond you see a hazard. There is no processing delay. It is a hardwired reflex.
But the watchdogs aren't just looking at the low-voltage coil, are they? They also use what's called sensing-based verification. During the 50-millisecond window when the car is just waking up, the system watches the main high-voltage bus.
Yeah, this is a beautiful piece of systemic cross-checking. You told the relay to close, so you expect to see the massive battery voltage rush into the system. If you look at it on a graph, the voltage should look like a steep hill rapidly climbing upwards.
But if that voltage stays flat at 0 volts with 0 upward slope, the computer knows immediately that the main contacts never closed.
Yes.
The relay is physically stuck open. And when it sees that flat line, it instantly aborts the entire startup sequence to save a component called the pre-charge resistor. Now wait, why would a resistor incinerate just because the main relay didn't close?
That requires looking at how an electric vehicle actually starts. You can't just take an 800-volt battery and slam it directly into the empty motors and inverters all at once.
Why not?
The massive, instantaneous inrush of current would act almost like a welder. It would instantly melt the metal contacts and weld them permanently shut. So engineers use a clever bypass route.
Like a smaller side door?
Exactly. Before the massive main relay closes, they open a smaller secondary relay that routes the power through a pre-charge resistor. This resistor acts like a bottleneck, slowing the electricity down and allowing the voltage in the motors to slowly fill up and equalize with the battery.
Oh, I see. It's like slightly opening a valve on a high-pressure water main to equalize the pressure before you throw open the massive floodgates.
That makes perfect sense, yeah. But here is the catch. That pre-charge resistor is tiny. It is only physically designed to handle that flow of electricity for a fraction of a second.
Oh.
If the main relay is stuck open and the driver tries to step on the gas, all the massive driving current tries to force its way through that tiny bypass resistor. It would glow red hot, catch fire, and incinerate within seconds.
Wow. So the computer detecting that flat 0-volt slope and instantly aborting the startup is literally the only thing preventing a fire.
It is.
It is incredible how tightly woven all these systems are. Like a failure in one spot instantly threatens another. But my absolute favorite part of this entire digital watchdog architecture is the ultimate safety net. They call it the doer checker lockstep.
The heterogeneous dual-core architecture. This is a foundational philosophy in high-reliability safety engineering.
The strategy is just brilliant. Inside the brain of the car, you don't just have one processor running the show. You have a main core, which they call the doer. The doer executes the driving logic. It reads the accelerator pedal. It tells the relay to close. It actually drives the car.
Mm-hmm.
But sitting right next to it on the silicon is a completely independent safety core, the checker. The checker doesn't drive the car at all. Its only job is to constantly audit the doer's math and independently monitor the physical sensors.
It is institutionalized paranoia built right into the silicon.
Yes. It immediately reminded me of the protocols on a nuclear submarine. When they need to launch a missile, it is never just one person pushing a button.
Yeah.
You have two commanders at opposite ends of the room who have to agree and turn their keys at the exact same time. It is built-in mandatory skepticism.
I love that comparison.
Right. If the doer says everything is fine, the relay is closed, keep driving, but the checker looks at the sensors and sees the auxiliary contact is open or the voltage is flatlining, the checker has ultimate veto power.
And it exercises that veto power with extreme prejudice. If the two cores disagree for even a fraction of a second, the checker physically pulls a safety pin on the circuit board in under 100 microseconds. It completely severs the low voltage power to the relay, overriding the doer entirely.
And when it does that, it logs a critical fault code and enacts what they call a soft lock. It flat out refuses to reboot the system.
Yes.
And the engineering notes explicitly state this is to prevent deadly electrical arcing.
Yes.
Which makes sense, because what is the very first thing a driver does when their screen goes black?
They try to turn it off and turn it back on again.
Exactly.
It is basic human instinct to assume it's just a software glitch. But if that heavy contactor is physically damaged, or if it's struggling against frozen sludge, repeatedly trying to force it closed with the massive battery power could cause massive electrical sparks across the tiny gap.
Oh, man.
That icing is literally plasma. It could melt the switch permanently shut, meaning you can never turn the battery off, or it could ignite a fire. The soft lock is the computer protecting the driver from their own troubleshooting instincts.
Okay, so having a paranoid digital watchdog is great for catching a fire before it burns down the car. But how do engineers design the physical hardware so the fire never starts in the first place? Let's move into the design phase. The DFMEA, Design Failure Mode and Effects Analysis.
DFMEA is basically where engineers sit in a room, imagine every conceivable way the universe could destroy their component, and then alter the physical geometry or the control software to make that specific failure mode mathematically impossible.
The first major design prevention they employ is heavy redundancy in armor. We talked earlier about those high-side and low-side drivers, the microchips that blow up from the electrical backfire. To prevent that, they use a dual independent control topology.
Right.
The high-side driver is powered by one completely independent power management chip, while the low-side driver is routed to the main microcontroller.
That physical separation ensures that if a rogue voltage spike manages to destroy one chip, it can't travel across the circuit board and destroy the backup path. But as you said, separation isn't enough. They also install literal armor, specifically TVS diodes, transient voltage suppression diodes.
These are designed to handle that water hammer effect, right? The collapsing magnetic field.
Precisely. When that massive reverse voltage spike hits, the TVS diode acts as an incredibly fast, highly calibrated lightning rod. The instant the voltage crosses a safe threshold, the diode opens up and absorbs the shockwave, bleeding the destructive energy safely away in a matter of nanoseconds, long before it can ever reach the fragile silicon microchips.
Okay, so the electronics are armored. But what about the heat trap? The joule heating that slowly cooks the enamel off the copper wire until it melts. I looked at the solution for this, and it is honestly my favorite piece of engineering in this entire deep dive.
Oh, the energy hack.
Yes. They call it pulse width modulation economizer control. I just call it the energy hack. Because I was looking at this and thinking, wait, if running the electromagnet at full power cooks it, but they need massive power to pull that heavy frozen switch closed, how do they cheat the physics?
They cheat it by recognizing that the physics of a magnetic circuit change dramatically depending on the physical position of the metal.
Right.
It takes a massive amount of magnetic force to reach across an empty gap of air and pull a heavy iron core toward the magnet, especially when you're fighting a stiff return spring.
So the strategy is to use 100% power, an absolute flood of electrical current, for exactly 100 milliseconds.
Yes, you need maximum brute force strength to get that heavy door moving and slam it shut. But here is the absolute genius of the design. Once the iron core has bridged the air gap and is physically touching the electromagnet, the magnetic circuit is completely closed. The air gap is gone.
Oh.
Suddenly, the amount of magnetic force required to simply hold the door shut is a tiny fraction of the force required to pull it shut in the first place.
That makes total sense.
Yeah.
So instead of keeping the pedal to the metal and cooking the coil, the computer drops the power to a 20 or 30% high-frequency pulsed signal.
Yes.
It turns the power on and off incredibly fast, just enough average energy to maintain the holding force.
And this isn't just a clever trick to save a tiny bit of battery range. This is about absolute thermal survival for the component. By dropping the effective current down to 20%, the heat generation, which remember scales exponentially with the current squared, absolutely plummets.
The data shows this drops the heat generation by over 70%. It guarantees that the copper coil stays at least 30 degrees Kelvin below its melting point, even if the car is parked in a desert at high noon with the air conditioning blasting.
It takes a component that physics dictates should slowly cook itself to death in a few hours and turns it into something that can operate continuously for a decade without ever breaking a sweat. It is an incredibly elegant, software-driven solution to a brutal thermodynamic problem.
And what about the physical wear and tear? The 1,000 Hz vibrations grinding the metal into dust and mixing with condensation to form that icy sludge.
For that, they turn to advanced materials. They redesign the internal guide tubes using self-lubricating polymers like PTFE, which is essentially industrial Teflon, or high-wear ceramics.
Okay.
By making the sliding surfaces inherently slippery at a molecular level, you drastically reduce the friction from the vibrations. No friction means no metallic dust. No dust means no sludge when the temperature drops to -40.
And just because engineers are paranoid, they don't stop there. They mandate that the return spring holding the switch open must be designed with a greater than 2 times mechanical safety margin.
Right.
So even if a little bit of friction does develop over 10 years, that spring is mathematically twice as strong as it strictly needs to be. It will brute force the contacts open when commanded, no matter what.
It's designing for the absolute worst-case scenario.
So we have a brilliant blueprint, we have lightning rods to protect the chips, we have energy hacks to prevent the melting, and we have indestructible Teflon armor. But a brilliant blueprint means absolutely nothing if it is built wrong by a tired worker on a Tuesday morning at the factory.
Oh, exactly.
How do you guarantee perfection on the assembly line?
That brings us to the manufacturing side of the equation, the PFMEA, process failure mode and effects analysis. The philosophy here is simple. You cannot trust the manufacturing process. You must verify every single step.
The standard is aggressively clear about this. It mandates 100% inline testing, not batch testing. They don't just pull one relay out of every 100 off the line to see if the machines are working properly.
No, batch testing works fine for manufacturing, plastic cups. It is fundamentally unacceptable for ASIL D safety components because the flaws you are looking for are microscopic.
Like what?
Well, imagine the robotic winding machine on the factory floor that spins the copper wire into a coil. If the tension arm pulls the wire just a fraction of an ounce too tight, the physical diameter of that copper wire stretches and becomes microscopic fractions of a millimeter thinner.
And thinner wire means higher electrical resistance.
Exactly. Or if the guide wheel on the machine has a tiny burr on it, it might put a microscopic scratch in the enamel paint on the wire, altering the magnetic inductance. The scanner detects these invisible microscopic manufacturing variations instantly. If the resistance is off by even a fraction of a percent, the unit is automatically kicked off the line into the scrap bin.
That's incredible. And the physical inspection is just as intense. They use acoustic microscopes and full 3D X-rays to inspect the microscopic solder joints that hold those critical driver chips to the circuit board.
People often think of soldering as just gluing two wires together so electricity can flow. But in an automotive environment, a solder joint is a critical structural bond. When the solder melts in the factory oven and flows beneath the microchip, tiny pockets of gas can sometimes get trapped inside the liquid metal.
Right.
When it cools, it leaves microscopic air bubbles, which engineers call voids.
And the specification is incredibly strict about this. It demands that the total volume of these voids must be less than 5% of the entire joint, and no single air bubble can be larger than 1%.
Yeah.
I was trying to picture why a tiny air bubble matters so much, and it hit me. It's exactly like pouring a massive concrete pillar for a highway overpass.
That is a perfect parallel.
If the construction crew leaves a cluster of air bubbles trapped deep inside the concrete, the pillar might look perfectly fine and smooth on the outside. But after years of heavy semi-trucks rolling over it and the brutal freeze-thaw cycles of summer and winter, those hidden air bubbles become stress concentrators. The structure flexing around the empty space causes microcracks to form. Eventually, those cracks connect, and the pillar completely crumbles.
That is precisely what happens on a circuit board. Under the extreme thermal stress of heating up and cooling down every time you drive, combined with that constant 1,000 hertz physical vibration, those microscopic solder voids turn into microcracks.
And a crack severs the electrical connection, the microchip loses power, and the entire relay fails.
Okay.
The 3D X-rays allow the factory to guarantee the structural integrity of the metal beneath the chip before the board ever sees a vehicle.
It's all about catching it before it's a problem.
Finally, at the very end of the line, just before it gets put into a box, every single relay goes through what I like to call its personality test.
A dynamic voltage test.
Yeah. The automated factory software slowly ramps the voltage up and then slowly ramps it down, measuring the exact millisecond the relay clicks closed and the exact millisecond it releases.
They're essentially mapping its unique mechanical fingerprint.
And the limits are tight. If the voltage required to release the relay drops by 15% from the golden standard, the software automatically halts the entire production line. Because a 15% drop isn't just a quirk, it means something inside the mechanical assembly is physically wrong.
Yes. It indicates that the heavy return spring might have been manufactured slightly weak, or the iron core is experiencing unexpected friction and feels slightly sticky.
It means that the 2x safety margin we discussed in the design phase has been compromised by the manufacturing process.
Exactly. They also use this test to check the precise microsecond delay of that little mirror contact sensor. The car's computer has a tiny 20-millisecond window programmed into its software to let the mechanical bouncing of the switch settle down before it reads the signal. The factory test proves that the physical switch perfectly matches the software's exact expectations.
Okay, so the system is designed mathematically, perfectly. It is built flawlessly on the factory line, passing every X-ray and scanner. Now we reach the climax of this engineering journey, the DVPNR, the design verification plan and report. Before a single one of these flawless blueprints is ever approved for mass production, a prototype faces an apocalyptic gauntlet of validation tests.
This is a crucial distinction. The factory tests ensure every unit is built correctly. The validation tests ensure that the blueprint itself can actually survive the brutality of the real world over a 10-year lifespan.
And the tests they put these prototypes through are pure torture. The first one is a severe environmental and vibration test. They bolt the component to a massive shaker table, and they vibrate it violently from 10 hertz up to 2,000 hertz, hitting it with an acceleration force of 35 meters per second squared.
That is an immense amount of physical violence.
And while it is violently shaking, they put it inside an environmental chamber and swing the temperature from negative 40 degrees Celsius all the way up to a baking 125 degrees Celsius. And they don't just do this for a few hours. They run the pulsed electrical current through the coil, shaking and freezing and boiling it, for over 1,000 consecutive hours.
The goal here is to simulate an entire lifetime of the absolute worst possible driving conditions. Driving over washboard dirt roads in the freezing Alaskan winter and baking in the Phoenix sun, and compress all of that damage into a few weeks of continuous testing.
And the passing grade is almost impossibly strict. After 1,000 hours of torture, they measure the electrical resistance of the coil. It is only allowed to change by less than 1%.
Less than 1%.
There must be zero visible mechanical fatigue on the springs or the contacts. And that tiny little auxiliary mirror sensor, its signal delay must remain under 1 microsecond. If it blinks late by 2 microseconds, the entire design is thrown in the trash and they start over.
It is absolute proof of durability. It proves that the Teflon self-lubricating guides actually work, that the spring steel doesn't lose its temper under heat, and that those X-ray inspected solder joints don't develop microcracks when subjected to hellish conditions.
Then, they move on to extreme voltage margins. They force the relay to successfully pull closed using less than 9 volts of power while frozen solid at negative 40 degrees.
That specific test simulates a driver trying to start their car in the dead of winter with an old dying 12-volt battery.
Right.
The relay still has to generate the brute magnetic force to rip that frozen iron core through the icy sludge and close the contacts.
On the flip side, they bake it at 125 degrees Celsius and force it to cleanly snap open, even if there's still 1.5 volts of residual power trickling through the line.
That ensures that if the digital watchdog commands a critical shutdown, the relay won't be easily confused by a tiny trickle of leftover current and refuse to let go.
Yeah.
It guarantees that when the computer says disconnect, the physical disconnect is sharp, immediate, and absolute.
But all of this shaking, freezing voltage testing is just a warm-up for the final exam, the 12,000 RPM dynamometer test. The engineering data details a hardware-in-the-loop fault injection test, and it is a nightmare scenario.
Hardware in the loop means they aren't just testing the relay in isolation anymore. They take the actual computer brains of the car, the real relay and the real motor inverters, and hook them all up to a massive multi-million-dollar simulator that tricks the hardware into thinking it is driving a physical car down a highway.
They spin a mass electric motor up to 12,000 revolutions per minute. They put it under absolute full electrical load, simulating a heavy car accelerating at maximum power. And then, intentionally and maliciously, they pull the plug on the low-voltage control line. They simulate a sudden, catastrophic wire snapping at top speed. When I read this, my jaw just dropped. Think about the sheer physics of what is happening. You have a massive metal motor spinning at 12,000 RPM, pushing a heavy vehicle. That is an unfathomable amount of kinetic energy and inductive electrical energy swirling through the system. If you just brutally chop the connection, where does all that violent energy go?
It is the ultimate question of EV safety. An uncontrolled shutdown at that speed and power level is terrifying. If that energy is not managed perfectly, the sudden break in the circuit would cause massive voltage surges that would literally explode the inverters.
Or worse.
Yeah, the sudden change in the magnetic fields could cause the motor to inadvertently apply massive regenerative braking torque. It would physically lock the wheels of the car while traveling at 70 miles an hour. It would be a catastrophic loss of control.
But it doesn't. Because of that 60 millisecond safety window we talked about, the system catches it. The data shows that the instant the plug is pulled, the doer-checker computer diagnoses the fault. It instantly switches the motor inverters into a mode called active open circuit or freewheeling mode. It takes that massive, violent electrical field inside the spinning motor and gracefully, mathematically decays the currents down to zero.
The TVS diode lightning rods absorb the shock waves. The software unwinds the magnetic fields. The heavy spring rips the contacts open. Every single layer of safety we have discussed over the last half hour coordinates perfectly in a fraction of a blink of an eye.
And the acceptance criteria for this test are absolute. No electrical overshoots, no demagnetizing currents in the motor, and absolutely no wheel lockup. So after all the thermal physics, the exploding microchips, the concrete air bubbles, and the 1,000 hours of torture, what does this actually mean for the person sitting in the driver's seat? It means that if a wire suddenly snaps while you are accelerating onto the highway at full power, the most terrifying mechanical failure imaginable feels like, well, nothing.
Just nothing.
It just feels like a gentle, smooth loss of power. The dashboard lights up with a warning, and your car just glides safely to a stop on the shoulder of the road. No drama. No fire, no locked wheels, just a quiet, safe glide.
And that is the true triumph of this level of engineering. The driver should never, ever know how incredibly hard the system worked to save their life in that 60 millisecond window. The millions of calculations, the indestructible armor, the simulated paranoia, it all culminates in nothing more than a quiet, safe stop.
It really gives you an immense appreciation for the invisible, obsessive safety nets layered into the technology we use every single day. But before we wrap up this deep dive, there was one tiny detail buried at the very end of our research that I haven't been able to stop thinking about.
Oh, the note about the digital modeling.
Yes. The engineers casually mentioned that to figure all of this out, they use an advanced simulation tool to create a dynamic thermal-magnetic transient coupled model.
Right.
They use this software to perfectly map out the precise pulsing of the energy hack, the exponential heat rise, the magnetic pulling force, and the friction of the sludge, all entirely inside a computer, long before a single physical part is ever built.
Yeah, it's all virtual first.
Think about the profound reality of modern engineering. Before a single piece of copper wire is ever cut, before a drop of solder is melted in a factory oven, or a heavy spring is wound, this entire chaotic life cycle, the extreme heat, the exploding chips, the microscopic friction at -40 degrees, was already lived out, simulated, and perfected millions of times inside a mathematical universe.
It's pretty wild to think about it that way.
It leaves you pondering, as we drive around in these massive, heavy physical machines, trusting our lives and our families to these tiny, perfect little switches. How much of the physical world we interact with every single day was actually born, tested, and finalized inside a perfectly simulated matrix long before it ever touched our reality?
That is a very good question.
The next time you press a button and your heavy vehicle hums to life, take a second to remember the invisible hero under the floorboards and the millions of simulated lifetimes it lived just to get you safely down the road.